So now we're going to introduce Chi-Merge. This is a discretization algorithm based on correlation analysis. It is a supervised method, which means our goal is to best discretize a continuous variable based on the given class labels. Okay, so if we have already known let's see, certain days, the temperature and whether it's a good day to play tennis. We want to discretize the temperature based on our yes or no labels, whether that day is a good day to play tennis. The idea is to find the best intervals to discretize temperature so that the temperature correlates with the class labels the best. After data is discretized this way, in theory, any algorithm would have a easier time to classify, to create a model and classify future data. So as we said, the basic idea of this correlation is to use correlation analysis, specifically the chi-square analysis, to explore the correlation between the intervals and the class labels. Throughout the analysis, we will see many interval class contingency tables will be generated and tested. And we want to find whether that interval and the class label have some correlation. If we found chi-square value to be low, means no correlation, then we want to merge those intervals into a larger interval until we find a larger enough interval that correlates with our class labels. So the merge will be performed recursively until certain stop condition is met. So the one stop condition could be when all the chi-square values that we found among those interval class contingency tables are greater than the critical value, to indicate that now the intervals and class labels are correlated. Okay. So I'm going to use example to illustrate the process. Here we have a set of 12 samples and we have certain features, which is numerical. And we have class labels. So this is a binary class situation. Class label is either 1 or 2. Okay. So the idea, so initially we will make every observation an interval. So this interval F1, 1 falls in between of 0 and 2. 3 falls in between of 2 and 5. So you can see we can create artificial intervals so that every data point is in its own interval. Or needless to say, this F, the values in F is sorted from the smallest to the largest. Okay. So now initially we have this many intervals, then we're going to recursively try to merge them and see which one can be merged. Our base of merge is to detect the interval class correlation by using chi-square test. So here we will calculate chi-square test on every pair of adjacent intervals. So between 1 and 2, that's one chi-square test. 2 and 3, it's another chi-square test. 3 and 4 is yet another chi-square test. So what's shown here, the example show the 2 and 3 and 3 and 4 test. So right now every observation has a interval, and so this is the interval column. Those rows represent interval, and here the columns represent class. So in this interval, I think that was between 2 and 5. In this interval, how our class label was distributed, this interval we have one occurrence of class equals 2, so 1 is here. And in this interval, we have one account of class equals 1. So this is our contingency table. And we'll create those contingency table for every pair of intervals that currently we have. So those are two examples listed here. And we will perform chi-squared test on those. So remember how we compute chi-square. For this contingency table, we found chi-square equals 2. For this contingency table, we found chi-square is 0. So those chi-square values being small, meaning that they are not correlated. Okay, so the current interval and class labels are not very well correlated. And we do that, and I noted here that because we're always going to have this 2 by 2 tables, therefore our degree of freedom is always 1. If we set the significant level to be 0.1, then our critical value for chi-square will always be 2.7. Okay, so we hope that keep on merging those intervals. Eventually, we want to find those intervals that have chi-square value that's greater than 2.7. That would indicate that the intervals that we found correlates with the class labels. Okay. So here we did that pair, tested the chi-square on each pair of the intervals, and here is our chi-square values, and we will merge from the smallest chi-square value. Okay, so here 0 is going to be merged, so all those, this going to be merged. This has also a low, this pair also have a low chi-square, so they will also be merged. And lastly, here, the 3 rows here will be merged. After the merge, we're going to have a table that looks like this. And now our interval has grown a little bit. So we have some larger intervals cover multiple observations. Again, we will do interval and class contingency tables and continue test, find the chi-square values between pairs of intervals. So here are more values that we found it. Again, we're going to merge the smallest value. Merge the intervals that has the smallest chi-square. And this results in this one. After those merge is done, we find 3 intervals. And this time, when we do test between this interval and class distribution, we found chi-square values which is greater than 2.70. So both of those values are greater. So we believe now that those intervals correlates with our class labels. And then this is going to be the interval that we decided. We're going to discretize this series of numbers into 3 intervals or 3 bins. So values between 0 and 10 going to fall into bin 1. 10 to 30 going to fall in bin 2. And between 42 and 60 will be falling into bin 3. How you're going to label this bin, what's the new values in the discretized result? It's dependent on your task. You could call this 1, this is 2, this is 3. You could give them a nominal label. That would be your choice, depending on what mining algorithms that you need to use to continue your mining task. So this is one example showing how we can use supervised method, taking the class labels into consideration to discretize one feature. Another idea in discretization is to create concept hierarchy. Concept hierarchy is not new to us now because we have seen examples before. For example, we have a concept hierarchy in our data cube drill down and roll up example. One concept hierarchy could be from month to quarter to year. You can see month is the narrowest concept, then quarter is an upper level concept, and then year is yet another upper concept that covers intervals. So this way we create a concept hierarchy that would allow us to drill down or roll up. Concept hierarchy can be generated it can be specified by domain experts, or in many cases, there are some taxonomies, thesaurus, ontologies already been created that can be borrowed and used. A taxonomy, by definition, have this class-subclass relations. So, for example, you can have species, and a upper level concept species would be genus, and then family. So we can using that hierarchy to explore, for example, biodiversity data. It can also be generated from data set. In general, this method applies by using discretization method on numerical or ordinal data. Remember, we can perform discretization recursively, so we can generate that hierarchy. For example, we can probably use student grades as one example. We can have A, B, C, D, right? And then within A, we can again have A minus, A plus. So that creates a hierarchy. We can also use frequent counts for categorical data. I'm going to show example of that. This is a heuristic method. By heuristic, we mean the method works in some case. It has some trueness to it. I mean, but it's not. It cannot be theoretically proven, and there are known counter examples that does not follow this heuristic rule. So frequency count for categorical data to create a concept hierarchy is one of those examples. We're going to show that in the next slides, I think. Concept hierarchy can also be learned using natural language processing and machine learning methods. If you're interested in this area, you can search for ontology learning or taxonomy learning. So this is a method that first extracting concept from text and then try to match extracted concept through narrow and broader relationships. That would allow the abstracted concept to be constructed into a hierarchical structure using broader and narrower relations. So from nominal data, we can generate concept hierarchies. One example is to specify well, I think I should not call it generate, because sometimes it is generated, some other times it's given. So in this case, we all know that street is a narrower concept than city. City has many streets, state has many cities, countries has many states. This forms a a total order with assumption that not one state are governed by more than one country. So that would be a total order of those attributes. Um, domain knowledge and common sense can be used here to generate such hierarchies. Other times that we can enumerate a set of smaller concepts that forms a larger concept. So it's by using explicit grouping. So Urbana, Champaign, Chicago are all cities in Illinois. Um, we can also specify a partial set of attributes. Instead of having this complete set, we can have street is narrower than city. So a city can include many states. I mean, a city can include many streets, and one street only belongs to one city. We can also automatically generate some of the hierarchy. So this is example that's proposed, discussed in the book. It has, I mean, I talked about this. This is a heuristic approach, that there are counterexamples. So in a relational database, we can probably find that if you have those fields, country, province, or state, city, and street, you're going to find you have many, many more instances of street than cities, of cities than states, of states than countries. So this gives you some clue that maybe states cover streets. I mean, maybe city covers streets and state covers cities. Many cities in a state, a city can only be in one state. A state has many cities. However, we can see this is a heuristic approach because if we look at a weekday, month, quarter, and year, weekday is a narrower concept than month. A month is narrower um, than quarter, and quarter is narrower than year. But months have more distinct values than weekday. We only have 7 weekdays. We have 12 months. Right? So this heuristic may or may not work. And a lot of times you could have something or falling into this order. You have to understand, first of all, those things are all geological locations, geographic locations. Then you have to count those things and hope that you are not accidentally introduce something else strange into this hierarchy. Anyway, when you perform such analysis, the system produces something interesting that you need to manually curate to make sure that concept hierarchy generated actually makes sense. Okay, so we have so far covered all the topics. I think, I believe we covered almost everything the book covered, only that we organized in a different way. The last thing I want to mention are some tools. Orange is a very, it's a graphic-based library that you can use to construct workflows and to use many learning algorithms that we will cover in this class. Maybe after this class, you will find Orange to be intuitive to use. And obviously R is what we are currently doing, and Python is our, well, if I say R only and not Python, I think some people will be mad at me. So Python 2, I'm not in favor of any, but I think they both are very, very useful, especially for NLP. Python probably is more powerful. And there's lots of data cleaning tools. The one that I recommend you to check out is OpenRefine. So OpenRefine formally is called Google Refine. It's open source software. It has built a pretty wide user community. It's a spreadsheet-based application that allows the user to effectively clean up messy data. Especially, I think it's fairly it has a fairly strong support on the misnamed attributes and varied expression of attribute values. If you work with text data, you will have experience and it will drive you nuts by looking at people's name, same people's name being spelled differently, sometimes with initials abbreviated, and sometimes not, sometimes has initials, sometimes it doesn't, and sometimes first name is first and sometimes last name is first. So those kind of crazy things, OpenRefine provide a tool for you to fix those. It also works for have tools to help you to clean up your numerical data. A work with large data set with like 100,000 rows. It doesn't scale to many millions yet. Google Refine is it's a desktop application that once you download, it's running in your browser, but can be connected to many other services. So it's quite flexible. Many data science workshops have tutorials on OpenRefine, and I have found those 3 videos. I think, well, at least I want you to look at the introduction video, so you have some ideas exactly what OpenRefine is. If it is useful for you, you can look at further videos. I personally think it is a very powerful tool. Okay, here we can summarize what we discussed in chapter 3. It's a lot of concept and many methods. We don't use all the methods in one mining task, but those should cover the most commonly used techniques. And I want to remind you to check again the learning objectives and make sure that anything mentioned in the learning objective sounded very familiar to you. Okay, thank you so much for your attention. That's the last video I'm going to make on the chapter 3.